Welcome to today's session on baseline machine learning models. In this lecture, we'll build intuition for fundamental supervised and unsupervised learning algorithms. These models form the backbone of machine learning, and even though they are considered baseline, they are often highly effective when applied thoughtfully. Our goals for this lecture are 1. To refresh our understanding of the machine learning taxonomy. 2. To review baseline supervised learning algorithms such as linear models, tree-based methods, and support vector machines. 3. To review baseline unsupervised learning algorithms, including clustering and dimensionality reduction. 4. To discuss practical tips for choosing baseline models. 5. To understand the fundamentals of training data setup, evaluation, and interpretability. Think of this lecture as both a conceptual foundation and a practical toolkit. Remember that machine learning can be broadly split into two categories. Supervised learning, where we learn from labeled data, like predicting disease risk from patient features. Unsupervised learning, where we uncover hidden structure without labels, think clustering patients by genomic signatures, learning nutritional intake patterns, or identifying skin lesions that are odd. A key point is that supervised learning focuses on prediction, while unsupervised learning emphasizes discovery. The ultimate goal of machine learning is to extract meaningful patterns or structures from data. In vision tasks, this includes object identification, detection, and segmentation. In unsupervised learning, we rely on clustering or dimensionality reduction to simplify complex data. These approaches complement each other. Often, unsupervised techniques are employed for feature engineering prior to supervised modeling. And of course, we have the case of semi-supervised learning, which is a mixture of both, as well as reinforcement learning, where agents take actions on an environment to learn appropriate state transition and response patterns. Now, let's start with the most fundamental class of artificial intelligence systems, the generalized linear models, or GLMs. From these, we have distinct flavors. First, linear regression models, which fit a straight line to minimize squared error. Linear regression works by trying to draw the best straight line through a cloud of data points so that the predictions are as close as possible to the actual values. To measure how well the line fits, we calculate the error for each point, which is just the vertical difference between the predicted value, the point projects on the line, and the actual data point. Since errors can be positive or negative, we square them, so all are positive, and then we sum these squared errors across all points. This is the least squares error, LSE method. The algorithm then adjusts the slope and intercept of the line to make this total squared error as small as possible. A useful physical analogy is to imagine each data point connected to the line by a rubber band. The farther away the point, the more the band stretches. The line learns by shifting and tilting until the total tension of all the rubber bands is minimized, balancing the pulls from every point at once. This iterative adjustment, often done by gradient descent, is how linear regression learns the best fit. This type of model is easy to interpret but may struggle to generalize to nonlinear data. Flavors of this are Ridge and Lasso regression models. Then, logistic and Poisson regression models, where data may appear linear in small regions, but with more data, hidden complexity becomes visible, for example, a logarithmic or Poisson shape. In logistic regression, the idea is similar to linear regression, but instead of predicting a continuous value, we're predicting the probability of belonging to a class, for example, sick versus healthy. The model still forms a weighted sum of the inputs, but then applies a sigmoid curve that squashes the output into a value between 0 and 1, interpretable as probability. Errors are measured using a log likelihood function rather than squared distances. The model is penalized heavily if it assigns low probability to outcomes that actually occur. A good analogy is flipping a probability dial. The line shifts and tilts until the probability dial points closer to 1 for true positives and closer to 0 for true negatives, balancing tension across all outcomes like adjustable springs pulling toward the correct class. In Poisson regression, instead of modeling continuous outcomes or probabilities, we predict counts of events, number of hospital visits per year. Here, the model uses the log link function, so predictions are always non-negative integers, consistent with real counts. The fitting process, again, minimizes a form of error based on likelihood. It adjusts parameters so that the predicted distribution of counts best matches the observed data. A helpful analogy is to think of bins collecting marbles. The regression shifts the bin positions so the expected number of marbles in each bin, predicted count, matches the observed marbles in the real world, with the model continuously adjusting until the mismatch tension is minimized. Despite the name, logistic regression is a type of generalized linear model because the logit transformation of the probability is linear in the predictors. This distinction is critical. Logistic regression is linear in the parameters, even though the output probability curve is nonlinear. Generalized linear models remain widely used in health research because they provide interpretable coefficients and well-understood statistical properties. Next, Let's move on to decision tree models, which recursively split the data into branches. A single decision tree works like a flowchart that splits the data step by step, based on feature thresholds, much like a doctor asking a series of yes-no questions. At each split, or node, the algorithm chooses the question that best separates the data into pure groups, measured by metrics like Gini impurity or information gain. You can picture it like a sorting funnel. At each junction, balls, data points, are sent left or right depending on their characteristics, and by the time they reach the bottom, they're grouped into categories. A decision tree ensemble, such as a random forest or gradient-boosted trees, takes this idea further by combining many trees. Each tree sees slightly different data or learns slightly different rules, and their predictions are combined by voting or weighted averaging to produce a stronger, more stable model. This is like asking a panel of doctors instead of just one. Each has their biases and blind spots, but as a group they arrive at a more reliable consensus. In the context of mammography for breast cancer detection, a decision tree might use features such as lesion size, shape, margin sharpness, density, and patient age. At the root node, the tree could first split on lesion margin, e.g., smooth versus irregular. Then within each branch, further divide by density or size until the leaves categorize a case as benign or malignant. For example, a large, irregular, spiculated mass might lead the tree down the malignant branch, while a small, round, well-circumscribed lesion might be classified as benign. This kind of model is powerful because its logic is transparent. Clinicians can follow the path of splits to understand why a classification was made, which is particularly valuable in public health settings where interpretability and trust are as important as accuracy. Decision trees are intuitive and interpretable, but prone to overfitting. Another model type of this kind are random forests, which solve problems by averaging across many trees, reducing variance, and improving robustness. A random forest classifier is an ensemble of many decision trees, each trained on slightly different subsets of the data and features, a process called bagging. Because every tree sees a different version of the data, they each grow differently and make slightly different predictions. Instead of trusting a single tree, which might overfit or make mistakes, the random forest collects all the trees' predictions and then uses majority voting to decide the final class. For example, if you have 101 trees classifying a mammography lesion and 62 trees predict malignant, while 39 predict benign, the random forest will output malignant as the final decision. This is similar to a jury system. Each tree acts as a juror casting a vote, and the verdict is decided by the majority. The strength of random forests lies in this diversity. Errors made by individual trees tend to cancel each other out, leading to a more robust and accurate overall classifier. Another kind of models include gradient boosting methods, like XGBoost, which builds trees sequentially, where each tree corrects the errors of the previous one. These are among the most powerful baseline predictors in structured data competitions. An XGBoost classifier takes the idea of decision tree ensembles a step further by using boosting instead of bagging. Instead of training many trees independently and then voting, XGBoost builds trees sequentially, where each new tree focuses on correcting the mistakes made by the previous ones. In practice, the first tree might capture the most obvious patterns in mammography features, but it will make errors on the harder cases. The next tree is then trained specifically on those misclassified cases, gradually improving the overall model. Each tree is a weak learner, but when combined, they form a very strong classifier. The final prediction is made by adding up the weighted contributions of all the trees, not just voting, so some trees may have more influence depending on how well they reduce errors. You can think of it like a team of doctors learning in sequence. The first doctor gives an opinion, the second reviews the cases the first struggled with, the third corrects what both missed, and so on. Together, they reach a more precise consensus. This method is why XGBoost often achieves state-of-the-art accuracy in structured healthcare datasets, including cancer risk prediction from imaging features. Ensemble methods such as random forests and XGBoost revolutionized machine learning before deep learning, and they remain strong competitors in tabular datasets. Support vector machines, or SVMs, are another key baseline model archetype. They work by finding the optimal separating hyperplane that separates the classes. The support vectors are the critical data points that define the boundary. By using kernel functions, SVMs can capture nonlinear boundaries. SVMs often perform well in high-dimensional spaces, though they can be computationally expensive with large datasets. Primary component analysis, or PCA, is also a cornerstone of baseline unsupervised learning. It reduces dimensionality by projecting data onto directions of maximum variance. The first few principal components often capture most of the meaningful signal. For example, PCA is frequently applied to gene expression data, where thousands of correlated features can be reduced to a handful of principal components for analysis. PCA also underlies modern methods like TSNE and UMAP, which better preserve local structure for visualization. Unsupervised clustering methods, such as k-means or hierarchical clustering, allow us to group data into meaningful clusters. Association methods, such as knowledge graphs, uncover relationships between entities. These techniques are essential in global health applications. For instance, identifying subgroups of patients with similar disease trajectories. Navigating the selection of baseline machine learning methods, or in fact any machine learning technique, is not an easy task. For that, engineers tend to develop intuition for such selection. But to kickstart you on that, I recommend this nice chart that I like from scikit-learn, which includes tips and tricks for that I feel are very typical questions for which most folks interested in training machine learning systems for global health would have answers for. In this case, the very first question is whether you have more than 50 samples. If not, the answer is probably simply to collect more data, because in machine learning, high quantity of high quality data is fundamental. If you do have more than 50 samples, the next fork is whether your data is labeled. With labeled data, you enter supervised learning. If your task is to predict a category, classification, and you have fewer than 100,000 samples, you might begin with naive Bayes for texts or a linear SVC otherwise, with alternatives such as k-nearest neighbors, SVC, kernel approximations, or ensemble classifiers if those aren't working. With larger sample sizes, an SGD classifier becomes more scalable. If the supervised task is predicting a quantity, regression, then with fewer than 100,000 samples, you should ask whether only a few features matter. If so, try lasso or elasticnet, otherwise start with ridge regression or linear SVR. If those fail, move to SVR with RBF kernels or ensemble regressors. And if you have more than 100k samples, a scalable SGD regressor is appropriate. If your data is unlabeled, you are in unsupervised learning. For clustering, if the number of categories is known and you have fewer than 10,000 samples, k-means or Gaussian mixture models are suitable, while larger sets benefit from mini-batch, k-means. If the number of categories is unknown, small datasets can use mean shift or variational Bayesian GMMs, whereas very large sets are far harder to handle reliably. For dimensionality reduction, if you are just looking, and the sample size is under 10k, use randomized PCA, otherwise consider kernel approximation. If instead you are predicting underlying structure, algorithms like isomap, spectral embedding, or locally linear embedding, LLE, are recommended. In this way, the diagram guides innovators systematically from data availability and labels through problem type and sample size towards sensible baseline models, with clear fallbacks if an initial choice doesn't work. Also, when training any ML model, there are a few foundational considerations that is important for all of you to know, particularly if interested in systems for healthcare applications. First, always split your data into at least training and validation sets, and hopefully also a testing set. A common split between training, validation, and testing is 60-20-20, though exact ratios depend on dataset size. The difference between these sets are subtle, but very important. The training set is meant to be used to fit model parameters, while the validation set is used to tune hyperparameters, the variables that define the model and how the model learns, and assess generalization during development, while the test set is a held-out subset of data used only once at the end to estimate the model's unbiased performance on unseen data. There are also a few important concepts in validation strategies that are important for machine learning engineers, such as k-fold cross-validation, stratification, and external validation. K-fold cross-validation is when the dataset is split into k equal parts. The model is trained on k minus 1 folds and validated on the remaining fold, repeated k times. This reduces variance in performance estimates and is especially useful with limited healthcare data. Leave one out cross-validation is a special case of k-fold, where k equals n, the number of samples. Each sample serves once as validation, while all others are training, maximizing data use but at high computational cost, relevant in small medical datasets. Stratified cross-validation is a variant of cofold, where folds preserve the original outcome class distribution. This is crucial in healthcare, where class imbalance, e.g. rare disease versus healthy, is common, ensuring performance estimates are not biased. External validation is when there is an evaluation of a trained model on an entirely independent dataset from a different population, site, or time period. This is the gold standard in healthcare ML, demonstrating true generalizability and clinical robustness beyond the development dataset. Pay attention to sampling strategies to avoid bias. Data leakage, where information from validation leaks into training, is one of the most common mistakes. Of course, evaluation methods in machine learning depends on the task. For regression, relevant metrics may include mean squared error, MSE, root mean squared error, RMSE, and peak signal-to-noise ratio, PSNR. For classification, adequate metrics may include a receiver operating characteristic or ROC curves, and quantification of area under the curves, AUCs, with sensitivity, specificity, and full confusion matrices. Remember, accuracy alone is rarely a sufficient evaluation metric, especially in imbalanced datasets, which are common in healthcare. Here you can see an example of a hypothetical ROC curve and what curve shapes are associated with worse or better performance. Ideally, a perfect classifier would be a ROC curve with an area under the curve of 1. Furthermore, on the right, you can see the theoretical definition of a confusion matrix. A confusion matrix is a tabular representation comparing predicted and true class labels in classification, showing counts of true positives, true negatives, false positives, and false negatives. It provides the basis for key performance metrics such as accuracy, sensitivity, specificity, precision, and F1 score. This diagram shows how the choice of evaluation metric should follow directly from what you want to predict and the relative importance of errors. If your model outputs class labels, start by asking whether both classes are equally important. If yes, and the dataset is balanced, less than 80 to 90% in the majority class, accuracy is suitable. If the dataset is imbalanced, G-mean is preferred to balance sensitivity and specificity. When the errors are not equally costly, use F1 score. If false positives and false negatives matter equally, F0.5 score if false positives are more costly, and F2 score if false negatives are more critical, common in healthcare screening tasks. If your model outputs probabilities, use the Breyer score to assess calibration when you truly need probability estimates. If you want to evaluate ranking ability, choose PR-AUC when the positive class is more important or rare, and ROC-AUC when both classes are equally important. This structured approach ensures the chosen metric reflects the data balance, prediction type, and clinical costs of misclassification. Something important is to be careful in deciding what to use as evaluation for your models based on the specific use case of it, for public or global health. Hard class labels are typically a good idea when downstream workflows require a binary actionable decision at a chosen threshold. Calibrated probabilities may be best if you are looking for risk stratification, ranking, shared decision making, and threshold tuning. Do your research, due diligence, and choose appropriate scoring methods to convince yourself, your peers, and even regulatory bodies on the performance of your AI models. Such prognostic metrics may include accuracy, a simple but potentially misleading score under class imbalance, F1, which corresponds to the harmonic mean of precision, and recall, which balances both. Beta, which in this case, set to F0.5 when beta is set to 0.5 to emphasize precision and avoid false positives, or F2 when beta equals 2 to emphasize recall to avoid false negatives, is helpful in screening versus ruling in context. Quodium, ROC curves, precision recall, or PR curves, and their respective area under the curves. In this sense, ROC curves are very common to use, but in many cases, precision recall curves may often be more informative under heavy class imbalance, because ROC-AUCs may appear high even when the positive class is rare, which may deceive you. Accuracy-based metrics include things like balanced accuracy, Matthews correlation coefficient, or MCC, which is robust under imbalance, specificity, and negative predictive value, NPV alongside sensitivity, and positive predictive value PPV. Algorithm performance metrics are also important and may include those for discrimination. See statistic, ROC curves and AUC, calibration, slopes, and intercepts, learning curves, bias variance diagnostics, and stability across training epochs or folds. Cost-benefit metrics are important and may include the decision curve analysis, net benefit, evaluations, cost-sensitive confusion matrices, expected utility, avoidable costs, among others, which align thresholds with clinical or operational requirements. Computational performance metrics are also becoming very relevant in practical implementation of these systems. These metrics may include training versus inference latency, total achievable throughput, memory footprint, and flops per energy usage, which may be critical for edge clinical deployments. Alright, now that we have reviewed some basics of baseline machine learning models and methods of evaluation, it is also useful to recognize the existence of packages for quick benchmarking of these methods, for example Python tools like LazyPredict, which can automatically train and evaluate dozens of baseline models, including simple MLPs with minimal code, great for establishing a first performance bar. Similarly, various trends in auto machine learning are making these kinds of tasks increasingly easy and focused on the highest levels of abstraction. The caveat, though, is that one still needs to learn how to decide what kind of modeling approach is appropriate and verify that systems enforce proper cross-validation, patient-level splits, feature scaling pipelines, and guard against data leakage. So it is important you familiarize with those concepts as you explore automated baselining in machine learning and neural networks in later lectures. One final, but very important topic in baseline machine learning is the concept of interpretability, which has become critical in health applications, particularly for global health. There are various ways of achieving interpretability, starting from more transparent modeling approaches to things like GradCam and popular techniques such as SHAP or Shapley additive explanations, which is shown in this diagram. SHAP assigns each feature a contribution to a given prediction, grounded in cooperative game theory. It works across model types, from decision trees to deep neural networks. SHAP is powerful, but keep in mind its limitations. It assumes feature independence. It is not causal inference. It explains model predictions, not real-world importance. Humans often overinterpret SHAP plots, making up causal stories that the math doesn't support. In healthcare, SHAP is increasingly applied to clinical decision support. For example, explaining which biomarkers drive predictions in dermatology, endocrinology, or mental health models. For deeper study on these baseline topics, I recommend the following reading: Deep Learning by Ian Goodfellow, Yoshua Bengio, and Aaron Corville, particularly Chapter 5 on machine learning basics. And of course, hands-on practice with Google Colab, Python, scikit-learn, and other machine learning and data analysis packages which provide accessible ways to experiment with these algorithms and techniques. So that concludes our session on baseline machine learning models, where our goal was to reach both conceptual clarity and practical intuition for when and how to use these fundamental approaches. Thank you so much for tuning in, and we'll see you in the next lectures, where we will focus on neural networks and deep learning for global health applications.